I am Mr. Taru. In this formula, we are going to introduce the distance formula and show its relationship at the same time with a cousin formula, the Pythagorean Theorem. We're going to use the Pythagorean Theorem in our first example. We're going to do a total of 3. We're going to use it with the first example to sort of show you how we develop the distance formula and where it comes from, instead of just giving it to you and say, yeah, this works because I said so, and do a couple of examples. Okay, so let's get to it. The Pythagorean Theorem is, and if you haven't seen this before, I'll do a quick introduction. The Pythagorean Theorem says we have a squared plus b squared equals c squared. Well, what's a, b, and c? A and b are the two legs of a right triangle. And so A and B come together in a right triangle to make the right angle, the one in here in the corner that has a little square in it. That indicates that this is 90 degrees or a right angle. So this is side A and this is side B, and you can interchange that because this is addition and addition is commutative, so if you called this A and B, that'd be fine. So we have one leg squared equals another leg squared, and that is equal to the hypotenuse squared. Now the hypotenuse is the longest side of a right triangle. And that is indeed going to be the distances that we find in the 3 questions or the 3 examples we're about to do. We're going to be finding distances between 2 endpoints of a segment, and that segment is going to be, for most purposes, acting as the hypotenuse, or will be the hypotenuse of the right triangle. So c squared, the hypotenuse squared, that letter c is reserved for the hypotenuse, and that is the side opposite the right angle. It will be the biggest side. Pythagorean Theorem, you would have learned that at the end of your Algebra 1 course, and it is useful for when you're given 2 sides of a right triangle and you're trying to find that missing third side. You might know the 2 legs and looking for the hypotenuse. That is going to be the structure of our problems we do in this video as we develop the distance formula. Or maybe in Algebra 1, you might have had the hypotenuse and a leg and been working to find the other missing leg. Okay, so we'll get back to that in a second. Oh, this is just the beginning of a geometry course, so we are only going to be in this video doing or finding distances between 2 known points. I will not be doing any examples where I give you one coordinate of an endpoint, the distance of a segment, and then give you some, maybe the second coordinate is missing an x or a y value, and you have to find that missing variable. We're not doing those kind of problems in this video. That takes a little bit more advanced algebra than we're going to deal with in this point of our geometry book. So here we have a segment, and our segment goes from 2, 3 to 5, 9. So we want to find the length of this segment, but yet I haven't introduced to you the distance formula yet. All I've done so far is reviewed, hopefully something you've learned in the past, the Pythagorean Theorem. And the Pythagorean Theorem is about, well, right triangles. So let's do this. Let's drop a vertical line down from this endpoint and extend a horizontal line from this endpoint that's below it, and here we have a right triangle. Okay, so we can finding distances along a slant is difficult. Finding distance along a horizontal or vertical movement, you don't need a fancy formula for that. You can just count it off. But before we do that, I need to know what this coordinate is. So this coordinate here is, well, I just moved horizontally, which is not going to change the y value. So I'm at 2, 3. And now I'm at 3, 3, 4, 3, and now I'm at 5, 3. So you can see that this coordinate has the same y coordinate as this one over here to the left because we moved horizontally. The y does not change. This coordinate has the same x coordinate as this point because I dropped it down vertically, and when you go vertically, you do not change the x value, you only change the y value. Okay. If I want to know how long this green segment is here, hopefully you can see the colors, I don't need a formula, I don't need a distance formula, I can just count it off. From 2 to 5, that's starting at the first endpoint, count off when you start moving, 1, 2, 3. So this segment here has a length of 3. Now, that's fine because I can just, see it, but in a second I'm about to throw some variables in here. So to get to the variables that we'll have in the formula, let's not just count off and say that it's 3, but let's remember how we find the distances along like say a number line. It's the absolute value, and I'm going to leave that part off, But well, that's not. It's the absolute value of 5 minus 2. And 5 minus 2 is equal to 3. And the absolute value of 3 is 3. So that's length here is 3. And we find that by doing, when we move horizontal, we find that by subtracting the x values. And we counted off and got 3, and we subtracted the x values and got 3. Good? Okay, now if we go up the side, again, let's start with the counting idea. We're here, and that's 1, 2, 3, 4, 5, 6 units long. But when we move vertically, let's get a little bit more advanced here. When we move vertically, we're changing the y-coordinates. So if I want to find a vertical distance, I subtract, instead of the x's like down here with the 5 minus 2, I'm going to subtract the y's to find a vertical motion, a vertical distance. So this 6 can come from taking the 9 and 3, absolute value of 9 minus 3, and that's equal to 6. So we can count this vertical distance off and see 6, or we can, again, remember how to find, like say, the distance along the number line. Just subtract those numbers and take the absolute value, because we can't have a negative distance. So we're trying to find the distance of this white segment. We now know that from 2, 3 to 5, 9, we have a horizontal movement of 3. We have a vertical movement of 6. This slanted line is going to be a little bit longer than both of those measurements because it is the hypotenuse. It's opposite the right angle of a right triangle. Plus, we can just kind of see that it's a little bit longer than the 6. So we have the 2 legs of a right triangle. Well, if we have the 2 legs of a right triangle, we can use the Pythagorean Theorem to find that missing side. In this case, it's the hypotenuse. So we have, let's see here, a squared. Let's see, that's one of the legs, so that's going to be 3. And if you put the 6 first, that would be fine too. One leg squared plus another leg squared. So one leg squared plus another leg squared equals hypotenuse squared, the distance. 3 squared is 9, 6 squared is 36, and c squared is, well, we don't know. That's what we're trying to figure out. 9 plus 36. Well, 9 and 36 is 45. We're going to continue solving for c. We need to get rid of that power of 2. So the opposite of squaring a number, that's what power of 2 does, we're going to square root it. So we're going to square root both sides. And we get c is equal to the square root of 45. But I want to simplify this and not just get a decimal out of a calculator. So can I simplify the square root of 45? I can if there's a perfect square in here, like 4, which is 2 times 2, 9, which is 3 times 3. Oh, 9 goes into 45. So that's the square root of 9 times the square root of 5. 9 times 5 is 45. And the square root of 9 is 3. So 3 times the square root of 5 is equal to c. And maybe I'm going to pause this video and go grab a calculator real quick, because I want to make this a decimal just temporarily so that you do see the hypotenuse is indeed longer than the 3 and the 6. Okay, well, 3 times the square root of 5 is 6.7, and that is longer than the other 2 legs. So we have a reasonable answer. We should be right. Now here's where we finally get into developing the distance formula. I hope you understood the steps that I've done with the Pythagorean Theorem and counting off these numbers on our coordinate plane, and that made sense because now we're going to use the pattern that we have in all of this work to show you where the distance formula comes from. Let's take this, and I'll put all the changes in purple. You know, what if we, now sort of kind of forget that this is on a number line for a second, okay? Let's say that we didn't know that first coordinate. We didn't really know that it was 2, 3, and it was just some random x and y value. We're going to call this x sub 1 and y sub 1, okay? And let's say that we didn't exactly know that this was 5, 9. Okay, that it was just some other point, because we can find the distance between any 2 points, not just between these 2. So this was like an unknown x sub 1, y sub 1, and this now is going to be our unknown x sub 2, y sub 2. And this here is, let's see, if we move horizontally, we're not going to change the y-coordinate, so this is going to have a y-coordinate of y sub 1. And if we move vertically, we don't change the x-coordinate. So this point here of our right triangle, I still want to keep that relationship between Pythagorean Theorem and distance formula. This point is going to have an x-coordinate moving straight down from our second unknown point. Moving straight down is not going to change the x-coordinate. So we have x sub 2. Okay. Now let's change or take out these numerical values that we just did a second ago. And hopefully don't forget the pattern that we did there. How do we find a horizontal distance? We subtract the x coordinates. So the horizontal distance that we have here is the absolute value of x sub 2 minus x sub 1. Okay? And the vertical movement is a change in y. So the vertical movement here, how far is it from this unknown point to this unknown point? Well, that's going to be, we're going to subtract the y values to find the change in y, or that vertical movement. So it's the absolute value of y sub 2 minus y sub 1. We're going to be getting rid of these absolute value symbols here in a second. Okay, so remember how we had the numbers. Hopefully didn't have any mistakes or questions with that. Now I'm putting in some more generic variables in here and seeing that I am using the same pattern. So we have a leg that is length of x sub 2 minus x sub 1 with the absolute value. We have the length of another leg, which we found by just subtracting the y values, only this time we don't know what those y values are. So we have a leg here and a leg here. How do we find the hypotenuse? We square those two legs and we add them together and we get the hypotenuse. So keeping up this pattern I have with the numbers just so you can refer back to it. The 3 was one of the legs, so we have the absolute value of one of the legs. Let's use the x sub 2 minus x sub 1 and square it plus, whoops. Got to keep the absolute value symbols in there for a second. So that's one leg plus y sub 2 minus y sub 1 squared. Oh, I'm going to run out of room. So I do need to get rid of this. So that's one leg squared plus another leg squared equals the hypotenuse squared, or in terms of a, b, and c like Pythagorean Theorem, c squared. Okay. The reason why we need these absolute value symbols in here is because they're going to ensure that we don't say that there is a distance that is negative. You can't have a negative measurement. There's no such thing as weighing a negative number of pounds or stones. So we can't have negative measurements. Well, at this point with the power of 2, the absolute values are redundant. They're not going to do anything. If you have a negative number in here and you square it, like negative 3 squared is negative 3 times negative 3, which is positive 9. So these powers of 2 are going to cancel out any negatives that exist from our subtraction, making the absolute value signs redundant. So now I can simplify this and say it's x sub 2 minus x sub 1 squared plus y2 minus y1 squared equals c squared. Again, I'm using Pythagorean Theorem. I want to find the distance, which means I need to square root both sides. And the square root and the square are going to cancel out, leaving this with just being c. So, c, the hypotenuse of a right triangle, is, with some unknown or generic values for the endpoints of the segment I'm finding the distance of, ends up being the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And we know that as the distance formula. Cool. So Pythagorean Theorem and the distance formula are really the same thing. So now that hopefully you understand where this came from, and I didn't bore you too much tying the numbers together with the random variables, the unknown variables here, let's get to two examples that again involve some numbers and practice the use of this formula just to make sure that we have it. Thank you for watching. All right, I love doing that stuff, tying these concepts together. It gets me so excited. All right, now let's just use a formula. Here's the distance formula. Here's a couple of points. This one has fractions, so you know why I'm adding that. It's too easy to skip fractions in classes when students are struggling because they struggle, but you ever use a tape measure? Build anything? Fractions are all over the place. Cooking, you can't avoid them, and if you do, you're doing yourself a disservice. So we're going to take a look at one with fractions. All right, so it doesn't matter how you label these points. Just pick one as being point 1 and point 2 you might think this is unnecessary, and if you are really good with your arithmetic and following order of operations and placing these values correctly in the formula, maybe it is redundant or not necessary, but it does help to avoid careless mistakes to get those labels on there before you start plugging the numbers into the formula. It leads to fewer mistakes. The distance is going to be equal to the square root of parentheses x of 2, which is 5, minus x of 1. Now, there's a minus from the formula and a minus from the number that you're plugging in. So you should always use parentheses when you plug in numbers. Always use parentheses when you are substituting in expressions if you're doing algebra. We're going to plug in a -3 here. I'm going to make sure to use a set of parentheses here to wrap the negative. So I see the one from the formula and one from the number I'm plugging in. Plus, or squared, plus y sub 2, which is -2. Nothing out in front of there, so we can wrap that if you like. It's not going to do anything in this particular case. But y sub 2 minus y sub 1, which is 4. There's two negatives. The negative times negative is positive, so that becomes basically a plus sign. And we have the square root of 5 plus 3, which is 8 squared, plus, and you should keep that wrapped in parentheses, because if this number ends up being negative, like this one here, -2 minus 4 is -6 squared. If you did not use these parentheses properly, and you are dependent on a calculator, which is not a good idea, those new two-line scientifics or graphing calculators are very sensitive to the way that you type the values in. They use the syntax or the notation correctly. Without these parentheses, -6 squared is -36, because the only thing you're squaring is the 6. Well, we're trying to square -6. So if you don't wrap that up in parentheses, it won't square the negative, and you will get the wrong answer. 8 squared is 64. -6 squared, -6 times -6 is positive 36. That is the square root of 100, and that is equal to 10 units. Now, as you study through geometry, we're going to be talking about lengths, areas, and volume. Lengths are units. Volume is, or area is units squared. Like if you're buying carpet, say, it's sold by the square yard. And volume is cubic units, so pay attention to that. Over here we have fractions. So x sub 1, y sub 1, x sub 2, y sub 2. The distance is equal to the square root of x sub 2 minus x sub 1 plus y2 minus y sub 1. Okay, we do need common denominators. So what we'll do, a couple of steps here. These two negatives are going to cancel out again and make a positive. Negative times negative is positive. The 1 is going to combine with 1/2. So the 1 needs a denominator of 2. So I'm going to take the 1 and multiply the numerator and denominator by 2 to get our matching denominator of 2. So 2 times 2 is, or 2 times 1 is 2, and again 2 times 1 is 2. So our 1 is going to become 2 over 2. Here I need a common denominator of 3. So I'm going to multiply the numerator and denominator by 3 so I can get that to match in the denominator. And we get the square root of 2 plus 1 is 3 over 2 squared plus 2 minus, let's see here, this is 3 times 3, right? So 3 times 3 is 9. So 2 minus 9 is -7 over 3, which is squared. Make sure I haven't made some kind of careless mistake. No. Okay. When you square a fraction, like 3/2 squared is 3 over 2 times 3 over 2. 3 times 3 is 9, and 2 times 2 is 4. So you square the numerator and the denominator. 3 squared is 9. 2 squared is 4. Plus, I'm not going to have this plus and the negative come together and make a minus sign, because I have to do exponents before I multiply. If I were to just write that as a big minus sign, I would be doing a multiplication before exponents, and that's not the proper order of operations. -7 squared is -7 times -7, which is 49, over 3 squared, which is 9. And again, I didn't pick a very easy one here or make an easy one up. We need a common denominator again. What is the lowest common multiple between 4 and 9? 4, 8, 12, 16, 20, 24, 28, 32, and 36. What about 9? 9, 18, 27, 36. Oh, okay. There is our lowest common multiple. That is going to be our common denominator. So how are we going to make a 4 into a 36? We're going to multiply it by 9. How are we going to turn a 9 into a 36? We're going to multiply it by 4. And that gives us the square root of 9 times 9, which is 81, over 36. Okay, now 49 times 4 might be a little bit tough to do in your head, but it's only 1 away from 50. So 50 times 4 is 200. But it's not 200 because it's 1 less. It's 1 less 4 times. So it's actually not 200, but 196 over 36. Now, if you didn't catch that, mental math is really kind of best doing the opposite direction. Like if I was not going to round this up to 50 and do it that way, 4 times 40 is 160, and 4 times 9 is 36, and 160 and 36 is 196. Still a little bit of mental math, but it's easier to do mental math a lot of times from left to right as opposed to right to left like we do on paper. This becomes the square root of 36. Let's see here. 190 and 80. 190 and 80, I'm dropping the ones for a second. 190 and 80 is 270. Now it's 271, and now it's 277. Let me double check. Yes. I already have this worked out, of course, to make sure I don't make any mistakes, or try not to make any mistakes in the video. There are no perfect squares in 277, but 36 is a perfect square. The square root of 36 is 6. So, got a little nasty with the fractions and the arithmetic on that last one, but a little bit of practice never hurt anyone. I am done. That is the distance formula and how it relates to the Pythagorean Theorem, which I've now erased, so I don't know why I'm pointing. I'm Mr. True. Go do your homework.